Thank you very much. And let's welcome all our audience from international everywhere. In now have many different time zones. And in Taiwan now we are 8 p.m. and in the speaker time zone now is 1 p.m. So welcome everybody to join our machine learning in astronomy and space science webinar. This is our number 6 webinar, and this series is hosted by the Taiwan Space Union and is leading by Professor Ip, and then with our assistant Mengze Ziting help to organize this webinar. And the next webinar, we will transfer to NCU platform. So this one is our last one using the Taiwan Space Union resources. And thank you so much for the support so far. And today is our great pleasure to have Xin-Yue Sheng from the Queen's University, Belfast in the Northern Ireland. And then she is actually my younger classmate, 学妹 or 师妹 in Mandarin. Yes, because we both now studying Queen's. And she is under supervision by Professor Matt Nico. Matt is also my younger classmate. Back to the time we studied together in the Queen's. So today she will introduce her research interests in the machine learning application, especially classify those rare transient at their early stage, which is very important because we will go into the very big data air like the LSST. So her tool would be very powerful to use on such big data, and then to identify those spatial transient like supernovae or tidal disruption event in a very early time. So now I think we just all warm welcome to our speaker, Xin-Yue, and then please can start your webinar.
Okay, thank you so much for Janet's very excellent introduction. Good evening and good afternoon, everyone. My name is Sheng. Today, my topic is neural engine for discovering luminous events. And this is a classifier to identify rare transients from the host galaxy images, such as superluminous supernova tidal disruption events. Firstly, I want to briefly introduce myself. I'm Chinese. I graduated from Wuhan University and got a Bachelor of Digital Publishing. And then I go to University of Edinburgh to do a master in high performance computing with data science. And I think just during that year, I had an idea that I want to do something about astronomy, and machine learning applications on that will be a really good way to go into. And I gave a year and to work with my master supervisor, Dr. Nick Rose, and we published a paper in Aging Time Series Simulation. And then I got a chance to do a PhD in University of Birmingham with Dr. Matt Nicoll. And later, after 2 years, because Matt moved to Belfast, so I transferred there. It's kind of dramatic, like the whole path. I end up, hopefully, I will graduate in Queen's. Personally, I want to say that as a female researchers, and especially in Asian societies, I feel like it needs more encouragement to achieve what you really want to do. So if you have any classmates, like friends or students, and who struggled with the applications for a PhD or master or converting to astronomy field, you can let them to contact me by my email. So I want to say in general, its transients are diverse, so as researchers. Back to today's topic. So I'm going to talk about, firstly, what are transients, and superluminous supernova and TDE. And third is briefly talk about what is the LSST survey, and then introduce my classifier called needle, and then how we apply needle on the light laser platform. And finally is a very relaxing discussion about machine learning. Is it magic? So what are transient superluminous supernova and TDE? I'm sure like a lot of researchers like Janet will already know about it. So I'm just briefly talking about transients are the objects that show up in the night, like increasing in brightness and then fading. And we called all of these objects transients, such as supernova, variable stars, and other events. And there's one particularly studied object called superluminous supernova. I mean here is hydrogen poor because this is more of our interest. And it is 10 times brighter than normal supernova type 1, 100 times brighter than core collapse supernova. You can see from the graph that it has a very long rise time scale and could up to like 40 to 50 days and have like hundreds of days for the decay. The mechanism behind them is still a mystery, and there are a lot of models to studies about what they are, but more importantly is we need more superluminous supernova to statistically analyze what is behind them. And the feature is that usually happens in the faint dwarf galaxy with very high specific dark forming rate, low metallicities. And here is the graph that I stole from Matt Nichols' paper. And you can see like compare with normal supernova type 1 and core collapse supernova, the superluminous supernova take a very, very tiny fraction of the whole discoveries. And it's growing from 2010 to 2020. It benefit from large scale service such as CTF that really help a lot to discover a lot. And also pastels. And so currently there are over hundreds of discoveries, but compared with other samples, this number is still very small. It's definitely important for us to discover such very rare events at their early stage so we can allow the spectra to follow up. Another transient is called tidal disruption events, and it occurs when a star orbiting massive black hole at the center of a galaxy, when it gets too close, to get disrupted, generating a accretion around the black hole. And from the detection, you could see that it often happens at the center of a galaxy, of course. And it has a feature that before the peak, and it shows the bluer continuum. It is very important because it can study how the black hole accretion star. Now there are only 60-ish discoveries. The third chapter is LSST. Universe is a huge crowd. Just imagine like you're a child and you go to an entertainment park and you heard so many children crying, yelling, shouting, and they just don't end. And this is the very modern future of astronomy. Like you will see like the universe is actually very crowded. LSST is the Rubin Observatory legacy surveys of space and time, and there's a 8.4 meters telescope built up on the Chile. There are 4 missions: understanding the nature of dark matter and solar system, and mapping the Milky Way, and the last one we really focus on is the transient study. LSST will last for 10 years, and for the observing field, it covers the whole southern sky and part of the northern sky. It mainly have two observing field, and the majority is the wide fast deep field, take like 90% of the observing time, and the majority of the observing field. And the other one is the deep drilling field, which is also interesting, and it will have high cadence, but only take 10% of the observing time. So we mainly focus on the wide fast deep field. There are a lot of cadence strategies has come out. Basically, the rule is a pair of bands is taken as one visit. For example, GNR or RNI. It might have seasonal cadence, but it depends on like for each season how many detections you want in a group. It has 6 bands, so you could see from EG, R, I, Z, Y is very deep. It can observe very faint objects. After 10 years, this decade image can be even further fainter. LSST will allow a number of brokers to connect it to it and to achieve the real-time classification. So here's just a number of how many superluminous supernova will be found per year, about 10,000. And for the TDE, it's 3,500 to 8,000. That's a lot compared to what we already have now. And the more horrible news is for per night, over 10 million alerts will be generated. Thinking about per year, how many it will be. So it's literally very difficult to, if you really want to find the like 10,000-ish superluminous supernova from such a great amount of data. So here is my research. My classifier called Needle, which is actually an idea from Matt Nicoho and find needle in a haystack. And I find it quite interesting because in Chinese, there's also saying like find needle in the sea, which is extremely difficult. First of all, I want to say like, because LSST haven't started officially, so what we are using is using dataset from ZTF, Zwicky Transient Facility Broad Transient Survey. I'm going to briefly introduce why we're using this main dataset as the main resource. So the goal is the ZTF Broad Transient Survey to observe to achieve the classification of supernova by their spectrum. And it is by far the largest spectroscopic supernova survey. It can get all the transients brighter than the 19 magnitude to achieve the classification. So basically, it's the best data we have. For ZTF filters, they have G and R band. The depth can be up to 20 meg. They also I band, but I barely use that. And the cadence is very similar to LSST. It will cover the whole northern sky every 2 or 3 nights. It also provide real-time alerts that which is very similar to LSST alert format. A lot of broker has been built on that, connected to ZTF alerts, so they can just easily migrate to the LSST alerts. The data source for my needle so include the ZTF Broad Transient Surveys. From the time I started this research last year, and there is 5,700 objects in the data side. Besides that, there are some samples also from ZTF, but they're not covered in BTS. There are 71 superluminous supernova and 32 TDE from papers. And then there's another algorithm, which is called Sherlock, which is a boosted decision tree-based machine learning classifier, and try to classify the transients based on their host galaxies, and also cross-matching catalogs. With the great support of Sherlock and its builder, Dr. Deb Young, we are able to get all the likely host coordinates for ZTF objects. But this is not complete. I will talk about later. And then once you have the Sherlock predicted host coordinates, you can find them in the Pan-STARRS data release 2. This is another survey that cover the northern sky and with the fire bands, so we can get the magnitude and the colors of the host. Because the Pan-STARRS ones, the data was taken before 2014, so definitely there is no overlap between the ZTF one. Here's the logic pattern. So we're planning on to build on needle on laser to get the future streaming alerts from laser platform, and then to gain all the Sherlock coordinates and Pan-STARRS host magnitudes, achieve the prediction, and put it back as the annotation for each object. And in the near future, we want to process the LSST data for sure. This is the dataset classes. So you can see the majority of the dataset is supernova type 1. And the second could be supernova type 2. And they're straight envelope interacting. And you can see a very small amount of superluminous supernova type 1 and TDE. So in order to improve our needle at this stage, we just sum up like to call all the supernova not, which is not superluminous supernova type 1 is supernova, because we pay more attention to superluminous supernova. That's our interest. So this is the labeling. After labeling, we found that they are almost half of the superluminous supernova don't have the predicted host. And this is reasonable because superluminous supernova often reside in very faint galaxy, and some of them are not cataloged. With LSSC, definitely there are more host galaxy will be found, and hope that this will be improved. And for the others, and for the TD, naturally you can find a host just by the coordinates of the transient itself. And this is the metadata analytics. So we calculate the peak magnitudes and magnitude at discovery, the difference. We could see that there's a difference between the supernova one, superluminous supernova, and TDE. And for the time difference, you can see a larger difference is because the superluminous supernova climb really slowly, and followed by the TDE ones. So I just want to show that they are very helpful features for us to classify them based on that. And this is the host colors and offsets corner plots. And the separation arcsec means the projected distance from the TD from the transient to the center of the host. It's natural that TD have very small offset, and the others varies. So for the image part, before we feed into the classifier, we found that there are so many images with very bad quality, which will highly influence the training process. So I developed a image quality checker, which is a 2-layer Xin classifier to give the credits whether it's good or bad. So if it is very bad, we just remove them, don't use them at all. This is the needle inputs. So currently we will only use the peak image, but later we will consider all of them. So we fit in the science image and reference image. The difference image is a spot, so it might, during our research, feel like it's not very necessary. And for the metadata, we have two sides: the transient part, the magnitude at peak, magnitude at discovery day, the time difference, magnitude difference, and the ratio. And the peak recent means the current detection, and the last detection, the magnitude difference and time difference. For the host, we have the file bands magnitude for the host and also two colors. The difference between the peak magnitude of the transients and the host magnitude in R band, and also the offset. This is the needle architecture. So we have two layers of convolutional neural network to deal with the image data, and also a fully connected neural network to deal with the metadata. And then at later stage, we combine them together. After several dense layers, we get the outputs. Because our datasets are extremely unbalanced, you can oversample it, but for the image one, it will be really difficult. Even you do the flipping or rotating, I mean, it's still very difficult to get a very fair solution. So we choose the weighted loss function at this stage. We will give more weight to the TDE and superluminous supernova, and give less weight to the supernova one. And the experience proved that it worked out, actually. Another issue is based on we don't have many samples. We need to average the 10 models prediction. Basically, it's just because, for example, you have 60-ish TDE and you put 15 in your test set, the last 45. It's difficult to say like whether they have all the features you want the needle to learn. The experience also shows that the accuracy varies, because some objects are really easy to predict, some are really difficult. So the solution is we average 10 models predictions. We have unique random seeds, so we initialize the weights and bias in the neural network exactly the same. And then we randomly select objects to put them into the test set. There are two versions of needle. The first one is needle with only the transient information, so the image and the transient's magnitude. The second is needle TH, which added up the host magnitude as well. This is the results for the confusion matrix, and the left-hand side is a needle with only transient magnitude in R band. The right-hand side is the same architecture, but we train the data only based on object with host. Remember that we only have half of the superluminous supernova have host, right? So we could see that the left-hand side classifier benefits from the increasing dataset. And the next one is the needle with transients and host information. We could see that the TD has been increasing. The completeness has been increased from 0.56 to 0.6. You can see the large range from the lowest accuracy to the higher accuracy, and this is actually not due to the training of the needle. It's actually from the dataset themselves. And the last step, we also train a solely host classifier. You only use the host magnitude, which I think is a very small, tiny version similar to Sherlock. And we could tell that actually host can indicate that the TDE with very high accuracy, but also the purity is not high for sure. This is the completeness and purity. I used the dotted line for the needle only with transient magnitude and the solid lines are with transient and host. So you can see that for the purity, the TDE has been getting better with the host information, and also the superlunar supernova type 1 have higher purity once you have the host information, because they are faint. So after all of that, I think it's very important to do some interpretations, like why this is happening, like why it look like this. So we look like the individual objects, and we found out that some objects are really easy to classify with a very high accuracy, some are not. So the right-hand side is just a trial of currently what I've been doing. It's a TD objects predictions over 10 models, and for each columns, and you can see it's each model. The green one is I put it into test set, and the white one is they're putting the training set. We could see the offset is the difference between the average of the training prediction and the test prediction. So it can tell us that if the offset is very small, which means it doesn't matter if you put it into the training or test set, it always get very similar probability. But the train offset and test offset, which is the difference between your correct label and your current prediction, if both of them are really bad, it means that the object itself are really difficult to learn. And this is even a more messy plot. I apologize. So I called it TD parallel feature plot, which for each column, you can see there are several different features. Based on the previous table, I can set a threshold, like some are easy objects, some are difficult object. And then I plot this and shows that there are indeed difference between the easy and hard one. For example, not sure you can see this is blue, purple, this is green. And you can see like the easy ones always have bluer color. Also, you can see from the delta T discovery and the TD, with the easy TD often have shorter racing time. And this is scaled by the normalization. So the next chapter is laser and real-time prediction. What is laser broker? Laser is pronounced laser. I'm not sure I pronounced it right. It means flame and flash in Scottish and Irish Gaelic. And from the last conference with I met the great storyteller, Dr. Roy William, and he told me that there's a book which named Anne Leather, and it's a collection of very brilliant poems from the Gaelic literature. And this is similar to what Leather in astronomy is doing, is to deliver, digest, analyze, and provide useful information to researchers who need. This is a platform for researchers to ask questions rather than answer the question. And this is the UK-based broker for processing out SST streaming alerts, and now it is digesting the ZTF alerts. This is the website. You can see you have filters that you can use the SQL query to build up your own filter to get the ZTF objects you want. You have a watch list. There's annotators where I'm going to put my annotations on it. So just briefly introduce how to achieve the real-time pipelining. Firstly, you need to build a SQL filter query and annotators on Laser. You set up your group ID, top ID, which is related to Kafka streaming schemes, and you can connect it to Kafka streams, get alerts one by one, and then you find signs and difference image and the transient magnitude records and others, and then achieve the prediction, and you can send it back to the laser. So this is the needle currently working in the laser. We could see that for each object, we can give a class dict for each label at the probability. So you can query by the probability. For example, you only want like over 80% to be a supernova, and then it will be high purity. There are some examples that current needle has been doing. This is predicted as a TDE, and it's very likely because you can see it is at the center of the host galaxy, and it proves that our needle can identify such features. And this is actually not a superluminous supernova, but it has a very similar features. If you can tell that it resides in a very faint host galaxy. To be honest, I feel we focus more on the completeness of superluminous supernova. We don't want to lose one, rather than we just misclassify, just found another supernova type 1, and that's okay. This one is the very common one, the normal supernova. So yeah, definitely needle always give very high probability as supernova because they are large samples. So needle current stage is not perfect, and we are working on the next one. We're thinking about all early detections because a lot of luminous supernova classifiers is based on light curves, and we actually not really use the entire light curves at all. So we are thinking about maybe we should add them up and maybe use all the existing detections before reaching the peak, because if you're reaching the peak, there's no point to classify them. They already done the follow-up spectra. And then thinking about the multiple bands, because our SST have 6 bands and CTF have 2 bands, but we haven't really thinking about correlations between bands. That will be interesting to know. The third is the LST alert schema, because LST alerts at that night will only provide a very tiny pixel. So it's not like the full, that large image like science image. So maybe there's a question, are we going to use the sign image at all or not? This is a next step I would think about. And the last step is it efficient? Currently, I run it on my personal laptop and HPC platform, Kevin, which from my campus. But I will use a separate remote server in the near future, and also to think about data storage. The final part is the machine learning is magic, not in my eyes. So I have seen some people really ask me, like, can I use ChatGPT to write machine learning for me? Sometimes they ask me, like, if there is ChatGPT, then what you're doing? I mean, I still get paid, and I don't want to feel too pathetic because I still want to do a postdoc in machine learning field. But I want to say, like, it's really easy to ask ChatGPT to write a classifier for you. And of course, it's extremely easy. Online, there are so many documentations that you can copy paste and to make it work. But I think for astronomy field, the problem is not that. The problem is from your data set and your preprocessing part. It serves for your motivation, and it don't serve for how fancy your machine learning algorithm would be. So I have some questions I have been thinking about. The first one is, so your data sets, are they real or simulated? If it is simulated data, then maybe it's a huge amount. You can generate whatever you want. You have the model. But there's a bias between the real and the simulated ones. Maybe you're aware of that, maybe you don't aware of that. For example, the AGN time series I'm familiar with. Currently, they use the Kalmar model, but it's stationary, but can't really expand the AGN flares. So another point is, once you use the simulated data set for training, you have to do the transfer learning to try them on the real data set to see how it goes. I'm sure that will be a burden for most classifiers. The second is, if it's real data, then there will be less amount of data for sure, and the quality, as we show today, it varies, and you have to deal with a lot of data pre-processing work before fit into your model. And the second is, are the data trustworthy? So there are a lot of data sources, Open Supernova Catalog, or some like million AGN mailing quasars, but some catalogs have very high completeness and very low purity, relatively low purity. And when you label them, you should be careful, because the data itself might be not the real label. Also, based on the data you have, do you think you have enough amount of data to achieve the feature representation? It could overfitting for your training set, but once you move to another data set, it might show like not as good as the results as you have right now. And third one is dealing with the vacancies. So we all know that the non-value cannot be fit into the neural network. Are you going to replace the non-value by 0? I mean, I have been doing this, but I still feel wrong. And I try to find another solution. So because 0 has physical meanings in astronomy field, of course, you can use the Gaussian process, or you can think about another models to do that. But it's always trade-off. The final is how efficient to get the data before you fit into the classifiers, how much time you spend on the data processing, and how you're going to store your data. The last chapter, the last slides will be machine learning is useful, but it's not magic in my eyes. As we said, that it's super easy to make a model work, but it's challenging to find that really suits what you really wanted. And the question is always related to your motivation, like why you want to use this model to achieve this. The second is how much credit to give. Do we really trust all the results? Like, do we trust the classification results at all? Or machine learning, you can just treat it as an assistant to give you the probabilities, and it's human who take the responsibility to check them. I'm sure it will be extremely difficult if the data is getting huge and huge, but where is the balance? I don't know. And we'll come to discuss. The third is, how do we understand? Well, machine learning, especially neural networks, you can think about it like a black box, but it shouldn't be. And I always came to interpret the models that I have been working on. Otherwise, I feel not safe. I feel like the real work of astronomical researchers should do is to understand how the machine understands the data. So the final one is still the same question: is it efficient? So the training process take longer. Prediction might be really fast, only a few seconds. But when the data get huge, to parallelize the data pre-processing part and data storage, and I think it's very important. Without SSD data, we don't know whether the current database can survive from that. Yeah, I think that's all. Thank you. Any questions? Welcome to answer.
Thank you so much, Xin-Yue, for your wonderful talk. So now and also great timing. So we have time for the discussions and questions. So we take questions from audience. You can either type your message in our chat, or don't be shy, just raise the hand using the button on the Google Meet. So before first hand raising, can I ask? So, do you think you can also use the needle to identify different subclasses of normal supernovae, like type 1A or type 2?
First of all, I think needle is built up by we know the features of superluminous supernova, and TD, we know the host can help. That's why we have very hybrid neural network. I think, as we said, that the model is served for our motivation. Of course, you can try to classify other stuff. I tried to classify the supernova type 1 and the others, but I think they're light curves, and there are more features that you need to think about, so you can modify the neural network, maybe. Yeah. So but in the future, we want to add up more subclass of supernova for sure.
Any questions from audience?
Yeah. So at some point you mentioned that from LSST you have 6 bands, and from Z you have 2 bands. So how do you dealing with this? So maybe they have different informations. Maybe
yeah, that's a really
the spectrum, or
yeah, that's a really good question. Honestly, I feel current needle cannot do that. I have been thinking about the correlation between 6 bands, because it definitely can tell. It's a simplified spectrum anyway. So if you, but the problem is only a pair of the bands are observed at the same time as one visit. So it will be difficult to fit into the neural network or any other machine learning algorithms. That's very interesting, but I think it's a very open question that I cannot answer right now.
So yeah, maybe we need to simulate the spectra for different, or do maybe 2D interpolation. So for for a bunch of transients with the same type, probably.
Thanks.
Any other questions? Yes, please. We have.
Hi, Sherry. Yeah, thank you for your wonderful talk and explaining your research to all of us. So I've got like 2 slight questions. So in one of the corner plots you showed earlier, there was some histograms getting overlapped between GR and R band or G band, if I'm not mistaken.
Let me just look at that.
Yeah, I mean, that beautiful corner plot had a lot of histograms and clustering of data points.
Let me see.
Yes.
Is it this one?
Yeah, this one. So let me just squint into the screen a bit more. So it's like SLSN is having some overlap with the TDE, right? For the GR and RI, if I'm not mistaken.
Yes.
So how would you interpret these results?
First of all, I want to say the supernova one can scatter all around in every plot, and this is reasonable. But we can still see the difference between TD and the superluminous supernova one by their offset, and also maybe slightly the different coefficients of the colors. Does it help?
Yeah, it does. Gives me some idea of this result. Okay, yeah, the other one, that one you mentioned was like, the one you mentioned is the messiest plot that you have in this whole presentation, with a lot of lines on the different parameters.
This one?
Yeah, this one. So I was wondering, what does this, like, as you mentioned that the y-axis is something scaled or normalized, something you mentioned. Yeah, so how does we interpret this, something that the easy line or the hard line is going to like about -2.5 for this delta Mach discovery?
I think for the y-axis, the -1 doesn't mean the value indeed is small. I think they just take the mean value at 0 and to normalize from that, because I think for each property they have different scalings of values. It's difficult to plot them on if you don't do the normalization, if that makes sense. So we can only see the thing is to compare with the two lines. For example, G minus R, we can see the bottom line, the purple line is have smaller value compared with the green lines.
Thank you for your explanation.
Thanks.
Thank you. Yes, I was also want to ask this question about this plot.
Yeah. It's just a trial of how to interpret the models, but I believe there are further steps. Yeah.
Yes. Okay. Ken, please.
Yeah, I'm just kind of curious about your training set. Just remind me again, how many examples of each type are in your training set?
I think there, the training set.
Yeah,
that's a good point. So you can see from here. So for each version of needle, it will take 15 objects from each for the test set. The others are all training. So of these, quite small for superluminous supernova type 1 and TDE for sure. Yeah. I think that's also caused the accuracy, like particularly, how to say, just shake around. But yeah.
So these are coming from spectroscopically classified superluminous supernovae.
Yeah,
that happen to be in the ZTF footprint as well, presumably because you need the ZTF data.
Yes.
So including the peak image, etc. Yeah. So I mean, presumably these are being added to every day. So I don't know how often you augment your training set.
That's a good point. Going to do it after finish the paper.
It's a bit strange this year. Only 4 type 1 superluminous supernovae has been identified so far, which is really very low number. Yeah, I don't know the reason.
Is it a question?
No, just a comment.
Yeah, I was thinking you are the most
about adding
professional person to answer
that. Sorry, I have one more question.
Yes, please.
So, which kind of data are you playing with? I mean, you mentioned that you can use the real data or the simulated data. Have you ever tried to play with the plastic data set? Have you ever heard about that?
Yes. So I know plastic, and I feel a lot. I think this is not the only purpose of needle. So for example, image you can't simulate. There's no simulated image for that.
Yeah, so, they have light curves.
Yeah, but that's a good question. Maybe we could think about combine the simulated data set with the real data set. But honestly, how to? I'm still investing. I don't know. And also that really just very similar to the discussion of today's last chapter, like the difference between simulated and the real data set. Well, you use the simulated data set to avoid some difficulties you meet in the real data. So I feel even you have a huge amount of data to use, there is still some drawbacks you need to think about and how to deal with them.
Yes, yeah. From the simulated data, you have very good quality. But at some point, for the observations, you need to classify as early as possible. So at some point, you have very few observations. So yeah, that's very different. Yeah.
May I follow this question? When we say to classify them as early as possible, do you mean how many days after exposure?
How many days? So for our SST alerts, as we said, like for the night, it generates after 60 seconds. It will give a pixel size, several pixel size magnitude image and magnitude data. So only after 3 days we can get the 6 times 60 pixels image, and I feel this is maybe not the best. Maybe we will improve on that. But if you say like to give a high probability to be a TD or superluminous supernova, I think we were thinking about maybe at most 2 or 3 or 4 detections. So it will be a very short like us. We don't want to really wait for 6 or 7 detections, because at the time everybody know what they could be.
Sounds very challenging.
It's very ambitious.
Yes, but also very important. Yes. Yes.
Can you please elaborate further on 2 sides of the confusion matrix you presented? Correct me if I'm wrong, but do they imply that needle TH is better at identifying TD? Better. I satisfy the percentage of the correct predictions. Oh, that's a great question. Thank you so much. So, maybe I can show it. So we have the confusion matrix. I should say that with the host data, you better compare with this one and this one, because they have the same amount of training object. Compare with the needle with only the transient magnitude, we could see the accuracy increase. I think it's because of the increasing amount of data set, but I think you might be right as well, because without the host, maybe the completeness of supernova is higher. I think adding up the host definitely benefit a lot from identifying TD, and that is partly what we want. Also, the superluminous supernova completeness also increased. So let me think. You said it with the percentage of the correct predictions. I have higher expectations if I add more early detections to this model, because current needle is just a version 1 in general. Later, I want to add up maybe the first 2 or 3 detections to the needle, and I think it will gain a higher accuracy.
Yeah, if you have further comment, yes, thank you. Yeah, so I think we only have time for the last question, and thank you for those audience who already asking. So yeah, please, if there is any question, or we can also, can we write an email to you if
yeah, of course.
Yes.
As I said before, welcome emails to let me know if you need any help with your career as a female. You can ask Janet for sure. Janet is very excellent researchers. I feel like if you need any mental support or the PhD application, or any people you know that suffer from that, you can contact me. Yeah, I will try my best to help.
Yeah, thank you so much for your kindness and support our students. Yeah, especially for our junior members here.
Yeah.
Yes. So if no more question, I think I would like to take this chance to thanks to Xin-Yue again. Thank you so much for this wonderful talk. And yes, now audience also thank you for a great and interesting talk. I really feel our audience get inspired by your talk. And then thank you. Yeah, thank you so much. And now I hope you have a nice afternoon for all our UK, Northern Ireland friends. And thank you all to join this webinar. So we will see you again in the next month, and we transfer to the NCU for this webinar. So thanks again. So thank you so much, Xin-Yue.
Thank you.
Thank
Bye
you.
bye.
Thank you. Bye bye.
Thanks, Janet, and thanks, Sherry, for this organizing this one. Thank you. Bye-bye.
Thank you.